So let's find the electric potential when I have a distribution of charge. So if I have a rod right here that has an even distribution of charge, so we'll call this length L, and I want to find the electric potential at this spot right here. And what do we make L equal to 10 meters, and that distance right there, 3 meters. So when I have a distribution of charge, I know, and again, I'm going to let, when R is infinitely large, V is equal to 0 volts. Again, those V's are not the same. So my formula is KQ over R. However, R varies depending upon where I am. So calculus is going to be involved here, especially since I have a distribution. And so I pick some generic location right here. And this is some charge dQ. Now let's go ahead and make the total charge Q. So I know that the linear density, charge density, is equal to Q over L, but since it's a uniform distribution or even distribution, this would be the same as dQ over dL. Fitting in with the brainwashing, why don't we just make this x is equal to 0, so this becomes dQ over dx, since this is along the x-axis here. And so now I'm plugging into that. So I know that the potential at this point, because of this small little differential, in other words, dV is equal to k dQ over R. I have two variables here, and then that one right there. So I'm going to integrate both sides. It is a definite integral here, but I do need to get Q in terms of x, and hey, right there, I can do it. So dQ is equal to lambda dx. So I can plug that in here. R is the distance from here to here, so this is R. And this is at some location x. In other words, that distance there is x. In other words, x plus R is equal to 13 meters. And so R is equal to 13 minus x. So plugging into here, I have V, once I integrate from some 0 to V. I know the pure mathematicians really don't like that, but I'm doing it anyway because I'm doing physics. And so K comes out, and dQ is lambda dx over 13 minus x. Lambda is a constant, so I have K lambda integral of dx over 13 minus x, which is negative K lambda dx over x minus 13. Integrating, this becomes negative K lambda times the natural log of x minus 13. And we are doing this integral, actually, at this point right here, we have a single unknown, a single variable here, x, and so x goes from 0 to 10, 0 to 10, 0 to 10, 0 to 10. And so I have negative K lambda natural log of negative 3 minus the natural log of negative 13, which is negative K lambda natural log of 3/13 by the way natural logs work. And so this becomes negative 9 times 10 to the 9th. Lambda is Q over L, so let's come up with a value for Q. Let's make this 7 nanocoulombs. Why not? So 7 times 10 to the negative 9th over the length, which is 10, times the natural log of 3/13. And this is equal to, because this is a positive charge, I do expect my final answer to be positive. And so that is just at least a quick and dirty check. I know I have a negative sign here, but that's going to produce a negative as well. And I get 9.24 volts.